Hello class, my name is Dr. Samuel Karenga from the School of Pure and Applied Sciences, Department of Physical and Mathematical Sciences, and today's lesson we'll be looking at electromagnetic radiation. We will look at how we can use electromagnetic radiation for both qualitative and quantitative analysis. And the lesson, we will start with part 1 on electromagnetic radiation, and we look at the outline of the lesson. We will introduce electromagnetic radiation, and then after that we look at the relationship between energy, wavelength, and frequency. We'll also look at day-to-day applications of electromagnetic radiation, and then finally we will wrap the lesson by looking at the chemistry of vision. Now, before we go to the lesson, it is important for us to familiarize ourselves with some of the Greek alphabets that we shall be mentioning during class. For example, we shall use the letter alpha to denote absorptivity. We shall also be looking at the letter epsilon to denote molar absorptivity. We'll also be looking at the Greek letter lambda to denote wavelength. We'll also be looking at the Greek letter mu to denote the unit of wavelength. And we'll also be looking at the Greek letter nu to denote frequency. So, what is electromagnetic radiation? Electromagnetic radiation, which is basically what we call light, is a form of energy, which can actually be described by looking at either the wave property or the particle property. When we consider light as a wave, we think of phenomena such as diffraction, which is bending of light as light is encountering an obstacle. We also think of things like dispersion. It is basically the splitting of light using a dispersive element, probably a prism or a diffraction grating. Now, as a wave, electromagnetic light consists of perpendicular magnetic fields that are oscillating, and these magnetic fields are perpendicular with electrical fields, as we shall see in the next slide. And most of the interaction between electromagnetic radiation and matter, and in this case matter can be atoms, molecules, or ions, is described by treating light as a particle. In this case, you can think of phenomena such as absorption or emission of radiation. So, we are saying that light can also be described as a wave, and therefore we say whatever we are calling the electrical fields, the oscillating electrical fields, perpendicular with the blue magnetic fields, and this is the direction of propagation of the wave. And again, the fields, the electric fields and the magnetic fields are perpendicular to each other. Now, as we continue with the lesson, it is important also to describe a phenomena of light known as polarization. As all of us know, when light shines, light comes from different directions, and sometimes for us to make it useful for analysis, it is important to align or to orient this line into a particular direction so that we can use it for analysis. And so there is this phenomena we call polarization, which is basically trying to align or orient light into one direction. For example, when light is going through polarimeter, you can see light comes from the radiation source in different directions. And then we have what we call a polarizer. And now if you can see, the polarizer is only allowing the vertical component of the light to pass through. So any other component that is not oriented vertically will not be allowed to pass through, and therefore whatever we allow to pass through can be used for example, polarimetry. We'll be able to measure the rotation of that light, and again we can use it for analysis. So there are several ways that EMR, which is the electromagnetic radiation, which we refer to as light, interacts with matter. And one of the ways this happens is through either the electric field or the magnetic field. Now, for the purposes of this class, we shall stick to the electric field. But for other classes or for other uses of spectroscopy, we can see that light can also interact with matter using the magnetic field. So, as a wave, electromagnetic radiation is characterized by all the properties you can think of a wave. You can think of speed, you can think of velocity, can think of amplitude, can think of frequency, the phase angle, again, as we said, polarization, as well as the direction of propagation. Now, in this case, we see some examples, typical examples of how light is actually interacting with matter. For example, this is light going through a cuvette containing a solution. And you can see that the light can be scattered, scattering meaning the light is now being sent into different directions away from the direction of propagation. We could also see the concept of reflection, where light is sent back to the same direction it came from at the surface. We can also see absorption, where some of the radiation is absorbed by the solution, such that whatever is coming at the end of the cuvette is of lower intensity than what was incident. And we also have the concept of fluorescence. We shall be looking at this at a later class, whereby in this case molecules can absorb radiation, they can be promoted to higher energy level, vibrational energy levels, and then they can relax back and they can emit energy in the form of fluorescence. So, as we think about electromagnetic radiation, it is also important to understand the electromagnetic spectrum, which is basically now the dividing of these electromagnetic radiations to different regions based on wavelength or frequency. And as we can see, the electromagnetic spectrum is actually spreading these regions from the high energy region of X-rays all the way to the ultraviolet, the visible region, which is the region all of us can be able to visualize, spanning all the way from the blue region to the red region, and we have the colors of the rainbow. And then from there we have the infrared region, and this is in the form of thermal energy, which can also be given off by molecules. We also have the microwave region all the way to the radio and TV, where we have the radio frequency, and these are long wave energy transmitted. So after looking at the electromagnetic spectrum, it is important now to look at the different sections of the electromagnetic spectrum and look at the applications in analysis in spectroscopy. We have the most energetic, the gamma ray region. In this case, we have gamma ray emission, and this usually probes the innermost nuclei of the atom. Then we have the ultraviolet region and the visible region. The visible region is where all our eyes are able to detect the colors of the rainbow. In the ultraviolet, we can have the vacuum ultraviolet, and then we have the visible region. Again, we use it for the UV vis absorption emission and also for fluorescence. And this one probes the electronic shells of atoms. In this case, when an atom absorbs energy in the form of ultraviolet visible, the electrons in the electronic energy shells get promoted to higher energy levels, and that is now what we call absorption spectroscopy. Now, these electrons don't stay in the excited state forever. They relax back to the ground state, and when they relax back to the ground state, they emit energy, and here we have atomic or molecular emission. We then have the region of the infrared region. In this case, we probe molecular vibrations and molecular rotations. And this region is useful in infrared spectroscopy as well as Raman spectroscopy. Then we have the microwave region. In this case, we have microwave absorption. We also have electron paramagnetic resonance, also known as EPR. And in this case, we are probing the magnetic induced spin states. Finally, we have the radio frequency. And in this case, we use it usually in nuclear magnetic resonance. Again, we are probing the property of magnetically induced spin states. Now, as we said that light can behave as a wave, so it has all the properties that we can think about of a wave. Think about things like wavelength, and wavelength defines the distance that it takes that wave to complete one whole cycle. Again, wavelength is denoted by the Greek letter lambda, and we say it's the distance between two consecutive maxima or minima. There are several units that we usually use to describe wavelength. The SI unit is the meter. We could also use nanometers. We could also use micrometers. And we could also use other we could also use other units to describe wavelength. So maybe the next question we can ask ourselves, what is the relationship between wavelength, the speed of light, and the velocity of light? And very soon we shall differentiate between the speed of light and the velocity of light. Now the wavelength is related to the speed of light and the frequency in this fashion, whereby the wavelength is equal to the speed of light divided by the frequency. Or you could also describe it in the form of velocity. In this case, the wavelength will be equal to the velocity of light divided by the frequency. And then there is another unit that we also needed to define, referred to as the wave number. And the wave number is actually the reciprocal of the wavelength. It's 1 over lambda, and it has units of per centimeter. And again, as we said, wavelength can be expressed in different units, and we shall encounter this in our class. You can use nanometers, we can use micrometers, you can use angstroms, which is equivalent to 1 times 10 to the power of 10 to the power minus 10 over meter. And we could also use other units such as picometer. So, let us now differentiate between speed of light and the velocity of light. When light travels in vacuum, we define that as traveling with a certain speed. And this speed has been experimentally determined to be 2.99792 times 10 to the power of 8 meters per second. Light can also travel in any other medium apart from vacuum. And in this case, we define the light as traveling with a certain velocity. The velocity is less than the speed. But if we look at the difference between velocity and the speed of light, it is quite small. It's less than 0.1%. And in this case, it has been acceptable to use 3.00 times 10 to the power of 8 meters per second sufficiently to describe the speed of light. And we don't have, in this case, to worry about the velocity. And therefore, now we have the relationship between the speed of light, which is what we are calling the 3.0 times 10 to the power of 8 meters per second. You multiply this by the frequency and the wavelength, and that now gives you the speed of light. Let us look at a typical example to illustrate this. So we are told different colors have different wavelengths, and the human eye is most sensitive for light of a wavelength of 555 nanometers, which is the greenish yellow in color. And the question is, what is the wavelength of this light in millimeters? And so now we can use the relationship that we know about wavelength and the several units. And first of all, we are expressing now wavelength that is given. It is given in nanometers, 555 nanometers. And the first thing that we do is to convert that wavelength into the standard unit, the meter. And we know that for every 1 meter, we have 1 times 10 to the power of 9 nanometers. And you can see up to this point, we have nanometers and nanometers cancel, such that now we are left with the wavelength in terms of meters. Next, we can convert that wavelength into centimeters. And we know that for every centimeter, 1 centimeter is equivalent to 1 times 10 to the power of minus 2 over meter. Again, up to this point now, we can see we can cancel the meter, and we are left with the wavelength in terms of centimeters. And the next step then is now to convert the centimeters into millimeters. And we know that for every 1 millimeter, it is equivalent to 1 times 10 to the power of minus 1 over centimeter. And again, up to this point, we cancel the units, we cancel the centimeters. And finally, we have the wavelength in form of millimeters as 555 times 10 to the power of negative 4 in terms of millimeters. Let us now look at frequency. So frequency is defined as the number of waves per second that pass a given point in space. In other words, we can also describe it as the number of oscillations in the electric field per unit time per second. And therefore, the unit for frequency is 1 oscillation per second. Usually you'll see it written as per second, which is also equivalent to 1 hertz. Now, the frequency of the wave is directly proportional to the energy of the wave. And therefore, we have the expression E is equal to H, the Planck's constant, multiplied by nu, the frequency, which is also equivalent to the Planck's constant multiplied by the speed of light divided by the wavelength. Remember, we had seen earlier that frequency is related to wavelength. There is an inverse relationship between frequency and wavelength. And we can also describe this energy in the form of the wave number. Remember, we defined the wave number as the reciprocal of the wavelength. And therefore now, if we multiply the Planck's constant, we multiply it by the speed of light c, and then we multiply this by the wave number, we are able to get energy per photon. Remember, we defined energy as a particle, a photon of energy, a photon of energy, a packet of energy. Now, H is the Planck's constant, and it has a value of 6.626 times 10 to the power of minus 34 joules second. There are several ways you can express frequency. You can express it in form of hertz, kilohertz, megahertz, which is 10 to the power of 6 hertz. We also have the gigahertz, again 10 to the power of 9 hertz. Let us look at a practical question on calculation of frequency. And in this case, you are given a wavelength in form of the wavelength of a microwave radiation, that is 1.07 millimeters, and you are required to calculate the frequency. We remember that the relationship between frequency and wavelength is given, whereby frequency is equal to the speed of light c divided by the wavelength. And again, we fit in the numbers and the constants, and we are able to calculate the frequency as 2.80 times 10 to the power of minus 11. And again, notice the units of frequency per second, which is also equivalent to hertz. Now, we've been defining energy of a photon, just 1 photon of radiation. What about if you had a mole of photons? So the energy per photon is given by the expression that we have just seen previously in the last slide. The energy of a photon is equal to the Planck's constant times the frequency, can also be equal to the Planck's constant times the speed of light divided by the wavelength, or could also be expressed in the form of the wave number, the reciprocal of our wavelength. So the next question we can ask ourselves, how then do we calculate the energy per mole of photons? And in this case, we have to remember the Avogadro's number, which is now what we are calling the N subscript AV. The Avogadro's number is 6.023 times 10 to the power of 23 photons per mole. Meaning now, if we multiply the energy per photon with the Avogadro's number, then we get energy per mole of photons. And that is now the expression we are seeing here. Energy per mole of photons is now going to be equal to the Planck's constant multiplied by the frequency and again multiplied by the Avogadro's number. It could also be equal to the Planck's constant multiplied by the speed of light divided by the wavelength, and then you multiply the whole of that with the Avogadro's number. Or if you decide to use the wave number, again it is equal to the Planck's constant times the speed of light times the wave number. Again, you multiply this by the Avogadro's number. Maybe we can look at this by looking at a practice question. And here we see we've been given information of a laser light, like the one I'm using to point at the screen. That's a laser. And the laser here that we are given, which is red in color, just like the one I'm using, is 632.8 nanometers. And we are required to calculate the energy in kilojoules of 1 mole of photons of this radiation. So how do we go ahead and calculate this? We already know that the energy per mole of photons can be defined or can be defined as the Planck's constant. You multiply that by the speed of light divided by the wavelength, and then you multiply by the Avogadro's number. We've been given the wavelength. Already we know the speed of light because it is a constant. And we also know the Avogadro's number, again, which is a constant. And so we just need to fit in the constants into the equation. And then we fit in the wavelength, which is 632.8 times 10 to the power of minus 9 meters. And again, we are able now to calculate the energy in form of joules, coming to 3.14 times 10 to the power of minus 19 joules per mole. But the question required us to calculate the energy in form of kilojoules. Now, to convert from joules to kilojoules, then we will need to divide that energy by 1,000. A kilo is 1,000. And when we do that, we find now that the amount of energy is 3.14 times 10 to the power of minus 22 kilojoules per mole. Then we also have what we define as amplitude, and amplitude is basically the height of that wave, the height of that crest. And then we also have the period, and the period is the time in seconds required for one wavelength to pass through a given point in space. So now that we have looked at electromagnetic spectrum, the next thing we should ask ourselves is, how then is it useful in spectroscopy? Or why are we having this class of theory of spectroscopic methods, and we are first describing electromagnetic radiation? Spectroscopy is divided into two major categories, and we shall look at each of these categories. The first category is where energy is being transferred between a photon of light and the analyte. Now, the analyte is whatever sample or whatever matter is going to absorb radiation. We said it can be molecules, can be atoms, or can be ions, and you may have it in the form of a solution. The second category is we look at the changes in some characteristics of the electromagnetic radiation. For example, we may be able to look at a change in the amplitude, the height of that crest. Or we might also be able to look at the change in the phase angle, or it could be the direction of rotation. Remember, we define polarization, orienting light into a certain direction, orientation, and then we measure by how much that light is being rotated. Or it could also be the direction of propagation. Maybe the direction of propagation is changing. For example, if we have scattering or reflection, those are things that can change the direction of propagation of EMR. Now, in absorption of radiation, remember we are saying that this energy is being carried in the form of a packet. And this packet is what we are defining as a photon. And we are saying that this photon is being absorbed by the analyte. And so what happens when the analyte absorbs this radiation? The electrons in the atoms absorb the radiation, and they are promoted from a lower energy to a higher energy. Because they have been able to absorb energy, they become what we call, or we say, excited. They go to an excited state. So they are promoted from a ground state to a higher energy level, which we are calling the excited state. So the absorption of a photon of visible radiation causes a valence electron. Remember, in UVVs we said we look at the valence electrons, the outermost. And this electron is going to move from a lower energy level to a higher energy level. This is different from other forms of spectroscopy, such as infrared spectroscopy. In infrared spectroscopy, it's not that an electron is being promoted from an electronic energy level to a higher electronic energy level, but in this case, we have the chemical bonds in the molecule experience a change in vibrational energy. In other words, the molecule will go from a lower vibrational energy to a higher vibrational energy. Now, the intensity of photons passing through a sample containing the analyte can be attenuated. It can be reduced as a result of some of the energy having been absorbed. And so in absorption spectroscopy, we are trying to measure by how much has that radiation been attenuated, and we call this absorbance, and we shall define absorbance in the next lesson. Now, the energy levels of an atom are said to be quantized. And what do we mean by quantization? They can only assume discrete energy values. Assume yourself climbing a ladder. If you are climbing a ladder, you go from one step to another. You cannot stop in between. And that is the same thing we are calling quantization of energy. An electron can only be promoted from a lower energy to a higher energy, and it cannot stop in between. It has to go from one energy level to another full energy level. Now, absorption only occurs when the photon's energy matches the difference in this difference. And if we look at this diagram is describing different energy levels. We have what we are calling the E subscript 0, which is the ground electronic energy level. That is the lowest in energy. Then we have the first excited electronic energy level. We are calling it E1. And then we have a second excited electronic energy level. We are calling it E2. And what we are saying, an electron can only be promoted from E0 to E subscript 1. It cannot stop in between. Or it can go from E subscript 0 to E subscript 2, a full quanta of energy. Now, when this happens, when such absorption happens, we get what we call a spectrum, which is a plot of absorbance against the wavelength. And in this case, as you can see, this spectrum is giving us two peaks. And in spectroscopy, we study what we call the lambda maximum, the wavelength of maximum absorption, the wavelength that is giving you the maximum absorbance values. And so in this case, if we look at these two peaks, we are able to see that the absorbance of this peak is far much lower than the absorbance of this peak. And therefore, if you are doing analysis, you would select this one to be the lambda max, or the wavelength of maximum absorption. So what happens when atoms, or the electrons in atoms, absorb energy and the electrons go to an excited state? They don't stay in the excited state forever. We say they relax back to the ground state. Now, when this happens, when now the electron transits from E subscript 2 to E subscript 0, which is basically now the ground state, the same amount of energy that was absorbed, as we have seen in the previous slide, this is the amount of energy that was absorbed. The same amount of energy that was absorbed is now emitted, and we say the electron has emitted radiation. It has emitted a photon of energy. Again, if the electron had been excited to E subscript 1, it will come back to the ground state, again emitting a photon of energy, or the same amount of energy that it had absorbed. Now, the second category of spectroscopy, we said it can cause a change in the amplitude or polarization or direction of propagation. And we have several representative spectroscopic techniques, such as we've already defined some of them, things like polarimetry. In this case, you are looking at the change in a direction of rotation of light, and so many other techniques. So, we've been talking about spectroscopy. We've been talking about absorption. Where does this energy that is being absorbed come from? And so now, we look at the sources of energy, and we start by saying all forms of spectroscopy that we have looked at this class require a form of energy. There has to be photons that will be absorbed. and these photons are coming from a source. In absorption and scattering spectroscopy, the energy is supplied by photons. And these photons, again, are forms of electromagnetic radiation or light. For case of emission and luminescence spectroscopy, such as fluorescence, chemiluminescence, and phosphorescence, the chemical energy to promote the analyte comes from a photon that has been absorbed from, again, a source. And in this case, the photon that is emitted, again, is emitted as the molecules are coming from a higher energy level to a lower energy level, thereby emitting energy in the form of photoluminescence. When we consider sources of radiation, a source of electromagnetic radiation must be energetic enough to give you an output that is both intense. Intense has enough energy that is going to be absorbed, and it also means to be stable in the desired region. It has to give you a stable output. All the energy that is being given has to be stable over the region of the electromagnetic spectrum that you are trying to do analysis in. Now, for sources of radiation, we classify them as either line or continuous. A continuous source is a source that is giving you wavelengths continuously, covering a wide range. And that is different from a line source, because a line source will emit energy in the form of very narrow selected lines. These are several continuous sources classified according to the wavelength region and also the usefulness in terms of what do they probe. We divide them again into continuous and line sources. We see examples of continuous sources like hydrogen lamps, deuterium lamps. We have tungsten. We also have xenon, usually used in molecular fluorescence. We have the non-stick glower, the glober, the nichrome wire. And all these are useful in infrared spectroscopy. They give the thermal energy that will be absorbed in IR. Then we have line sources, for example, the hollow cathode lamp, useful in the UV-Vis region in atomic absorption spectroscopy, whereby we probe the absorption of radiation by metal elements. We also have the mercury vapor lamp, again in molecular fluorescence. And we also have lasers, which are also quite energetic and quite intense. And these again are used in atomic and molecular absorption in fluorescence and scattering. In absorption spectroscopy, a beam of radiation passes through a sample. Much of the radiation is transmitted without a loss of intensity. However, at selected wavelengths where the sample can absorb, the intensity of that radiation is attenuated, and this is what we are referring to as absorption. There are several, or there are specific requirements for absorptions to take place, and we've already mentioned some of them. For one, there has to be a mechanism by which the radiation's electric field or magnetic field is interacting with your sample. Is it interacting through the electric field? Is it interacting through the magnetic field for light to be absorbed? For UV-Vis, this interaction involves electronic energy levels, where valence electrons in atoms are promoted from lower energy to higher energy. In infrared spectroscopy, again, there is a change in the vibration of the bond in the molecule. In this case, the bond can be elongated or the bond can be compressed when we have these stretching vibrations. We also said that energy has to be quantized. And we said by quantization, it has to assume discrete values. Again, here we see different levels. We have the E1 and we have the E subscript 0. This is the ground state, and this is the excited state. Again, you can see energy can only be absorbed if the energy difference between one electronic energy level and the other electronic energy level matches the energy of the photon that is incoming from the source. Again, as we said, we also have vibrational levels in infrared spectroscopy. Again, vibrational energy levels are also quantized, and energy can only be absorbed if it matches the energy difference between two energy levels that are close. For example, V0, V1, or it can be V0, V2, a complete transition. Now that we have already looked at electromagnetic radiation, we've seen how electromagnetic radiation can be absorbed or emitted. It is important for us now to look at the spectrum. The spectrum is a plot of what we get after the light has been absorbed or emitted. And we need to define molecular versus atomic spectra. Molecular spectra is given by molecules. Atomic spectra is given by atoms. And we start by saying that atoms, ions, and molecules can only exist in certain discrete energy states, what we refer to as quantization of energy. Now, when these species absorb or emit energy, it is going to be exactly equal to the difference between two energy states. Only certain energy states are allowed. Again, we repeat the concept of quantization. And we now define the different energy levels that we can think about. We've already looked at electronic energy levels. Electronic energy levels are present in all chemical species as a consequence of electrons rotating around the nucleus. Atoms and ions exhibit this type of energy levels only. Atoms, ions, they only consist of electronic energy levels. Vibrational energy levels, these are associated with molecular species, and they are a consequence of interatomic vibrations. These vibrational energies are also quantized, meaning only certain vibrations are allowed. On top of vibrational energy levels, we also have the rotational energy levels. Again, these are associated with rotations of the molecules allowed their center of gravity. Again, these are also quantized. Now, in this diagram, we are going to see, or we are seeing all the energy levels. We have the electronic energy levels represented by the dark lines. All these are electronic energy levels. Again, we have the ground state energy level. We have the excited state energy levels. Energy increases this way. With every electronic energy level, it has associated with it vibrational energy levels. Then for every vibrational energy level, it has associated with 8 rotational energy levels. And one of the things we notice, the energy difference between electronic energy states is quite high, as you can see this difference. Compare that with the energy difference between vibrational energy states. The energy difference here will be quite small. And again, the energy difference in rotational levels will be far much smaller. If we now compare the spectra that results from purely electronic energy levels, and we compare this with the spectra emanating from an overlap between electronic, vibrational, and rotational energy levels, we will notice a very big difference. We have what we call the line spectra that is resulting from purely electronic energy levels. And this is where, again, we said we have atoms and we have ions. Atoms and ions will give us line spectra. When you consider molecules, because of now the overlap between the electronic energy transitions, vibrational transitions, and rotational transitions, molecular spectra are usually very broad. You get very broad peaks, as you can compare the broad peaks from molecules and the line spectrum from atoms and ions. And therefore, it becomes pretty easy for you to be able to differentiate between a spectrum that is belonging to an atom or an ion, because it will look different from the spectrum belonging to a molecule. Now, the electromagnetic spectrum. Again, we can express the range of all possible frequencies and wavelengths of electromagnetic radiation, and we assign it to arbitrary regions, and this is now what we call the electromagnetic spectrum. Again, we see the different regions. We have the gamma rays. The gamma rays are the most energetic. From the gamma rays, we have the X-rays that can be used for X-ray imaging. We also have ultraviolet radiation, an example that comes from sunlight. And then from ultraviolet, we have the visible region. Again, as we said, this is the region most all of us can be able to visualize. Then we have infrared, we have microwaves. We also have the radio waves, usually used for communication. Now remember what we said about the relationship between energy, frequency, and wavelength. Energy and frequency are directly proportional. And that's why we see gamma rays have the highest frequency. They are the most energetic. Compare that with the radio waves. They have the lowest frequency, but they have the longest wavelength. And for that reason, we are able to use them for communication purposes. So in this part of the class, we now look at the different applications of these regions of electromagnetic spectrum. For example, we have the gamma rays. As we said, the gamma rays are the most energetic. These are high energy electromagnetic radiation waves. We have a very small wavelength. Remember, wavelength and energy are inversely proportional. They are highest energy electromagnetic waves. And because of their very high energy, they can be used for sterilizing medical equipment, and they can also be used for treatment of certain cancer cells because of their very high energy. Unfortunately, they have the ability to kill even normal cells. We have the X-rays. X-rays, again, small wavelength, high energy, meaning high frequency, useful in medical imaging, and we can also use them. They are also widely used in screening bags at airports. Moderate doses can also be damaging to cells because this is a form of ionizing radiation. Next, we have the ultraviolet, shorter wavelength, also relatively energetic, used in security imaging, can also be used to sterilize medical equipment. Too much of it can cause sunburn. That's why you need to wear sunscreen when you go out in the sun. Then we have, before we go to the next radiation, maybe we can summarize this part and say the gamma rays, the X-rays, the UV. These are part of what we call ionizing radiation. They can disrupt molecules by ionizing the molecules, and they can actually kill cells or cause the cells to mutate or maybe result into the cell becoming cancerous. Then we have the visible radiation, which is a very small part of the electromagnetic radiation. The only electromagnetic wave can be detected by the human eye, spanning from the region of blue to the region of red. blue around 400 nanometers, and red around 700 nanometers. And for example, one of the phenomena that we usually see in an everyday application is the appearance of a rainbow as a result of the sunlight being dispersed. The radiation from sunlight, which is basically all the 7 colors of the rainbow, being dispersed by water droplets. Remember what we talked about, dispersion. And the result of that is we see a rainbow. We also have the infrared radiation, and this is useful in night vision goggles. You are able to see, maybe visualize game, wildlife at night, or they are also used by law enforcement. We also have them in remote controls. We have microwaves. Remember, these are long wavelength. They are long wavelengths spanning between a millimeter and a meter, useful in microwave ovens, Bluetooth headsets, the radar, and the global positioning systems. We have the radio waves. Radio waves, again, are long wavelength waves, useful in radio and TV broadcasting, also in cell phone communication alongside with microwave radiation. And we also have them useful in magnetic resonance imaging, which is a medical technique useful in taking images of body parts to detect damage. Maybe to wrap up this region, we can look at another question. In this case, we are considering the relationship between frequency, between red light and green light. And if you remember what we said about the electromagnetic spectrum and the visible region, we said the red region is around 630 to around 700 nanometers. The green region is around 520 to around 560 nanometers. And again, if you compare this in terms of frequency, we know that frequency and wavelength are inversely proportional, as we can see from this relationship. And therefore, as you would expect, the shorter the wavelength, the higher the frequency. Another question for a particular transition, and this is the change in energy, meaning the energy difference between electronic energy states, is given as 3.85 times 10 to the power of minus 20 joules. And you are supposed to calculate frequency of this radiation and also the wavelength. Maybe to start with the frequency, we know the relationship between energy and frequency by the use of the Planck's constant. So we know that energy is going to be equal to the Planck's constant times the frequency. And we can rearrange the equation so that we get the frequency equal to the amount of energy divided by the Planck's constant, and then we plug in the values. When that is done, we are able to get the amount of frequency as 5.81 times 10 to the power of 13 per second. And then now from the frequency, since we know that frequency and wavelength are again inversely proportional, we can be able now to calculate wavelength from the frequency and the speed of light being a constant. Again, we have the speed of light divided by the frequency, and we are able to calculate the wavelength as 5.16 times 10 to the power of minus 6 of a meter. Now, one of the applications of electromagnetic radiation is the qualitative analysis of elements. In this analysis, or in this form of spectroscopy, we look at the amount of energy that is being emitted by every element, and by looking at the wavelength of that radiation, we are able to detect different elements. And this happens as a result of what we have talked about absorption. When an electron in the ground state acquires energy, in this case
case in the form of heat. The electron is promoted to a higher energy level by absorption of energy. When this electron now comes back to the ground state, it is going to emit the same amount of energy that it had absorbed. And because we know the relationship between energy and wavelength, we are able to express this energy in form of wavelength as the electron goes back to the lower energy state. And therefore, by looking at how much radiation has been emitted in the form of a wavelength, we are able to detect certain elements. For example, commonly used in organic chemistry for the flame test, and we are able to detect the presence of halogens because of the green to blue color that they emit. We are also able to emit different elements based on the colors they emit. For example, sodium will absorb and emit yellow. Lithium will emit crimson lead, and we have metals such as copper, which will emit a bluish green flame. When we have solids, excited solids, again, will also emit radiation in the form of continuous radiation. Remember, we said continuous radiation is radiation comprising of all the wavelengths in the visible region. For example, gases will only emit specific wavelengths or lines, and therefore we have line spectrum. For example, this is the spectrum emitted by a solid, and you can see the emission is coming in the form of white light. It's going through a dispersive element. For example, a prism could also be a diffraction grating. And when this radiation is diffracted, you see it projected onto a screen, and you see it as a whole range of colors. You are not able to differentiate or say it is only green or blue, because it comprises of the whole range of the colors. And that's what we are calling a continuous spectrum. Compare this with what happens when you have a gas. For example, if you had hydrogen in a discharged tube, application of voltage, the hydrogen molecule will absorb radiation, becomes excited, comes back to the ground, becomes excited, can be disintegrated to two different atoms of hydrogen, comes back to the ground state, emits radiation. When this radiation is passed through a dispersive element, again in this case a prism, you can see now the light is dispersed into 4 different wavelengths. We have a wavelength that is red, green, blue, and purple. Again, when this is projected onto a screen, you are able to see a line spectrum. You can see discrete lines, specific wavelengths. An example of line spectrum. So again, we are saying from the hydrogen gas, light is absorbed or emitted from electrons moving between the energy levels. Only certain energies are allowed because of quantization of energy. And that's exactly what we are talking about, the quantization of energy. If you look at another element such as sodium, again, sodium in a flame. If you get radiation from sodium in a flame, again, you pass it through a dispersive element. You will see 2 lines that are very close. One line is at 589.0 nanometers. The other line is at 589.6 nanometers. And that is now what we are calling the yellow line of sodium. Now, as we conclude this first lesson, we do so by looking at the chemistry of vision. How are we able to see? And for us to be able to understand the chemistry of vision, we go back and refer to the color wheel. The color wheel has the primary colors, yellow, red, blue. And then we also have the secondary colors, green, orange, and purple. If we divide or we now arrange some of these colors in terms of the wavelength range, again, you can see it in this table. For example, if whatever color is being absorbed by your sample is in the range of 380 to 420, then the color that is being absorbed is violet. Remember, 400 to around 700 in the visible region. But the color that you are going to see is not actually violet. It is now the complement of what is transmitted. In other words, the complement of what is not absorbed. And so the color that you will see is green, yellow. Let's take a practical example. Let's think of a pigment such as chloroform. When you look at, not chloroform, but chlorophyll, I'm sorry. When you look at a pigment such as chlorophyll, it will appear as green. But does it absorb green? No. Because the color that you are seeing is the complement of what is absorbed. And as you can see, the lambda max for chlorophyll is around 663. Now 663 is in the red region, if you remember the color wheel. So the complement is the opposite color in this color wheel, which is going to be green. So when you look at chlorophyll, because it is absorbing red, it will appear as green. Let's look at another pigment such as beta carotene in carrots. When you look at a carrot, you see the carrot is appearing orange. Orange because it's absorbing the complement of orange. And the complement of orange, the lambda max of beta carotene is around 455 nanometers, which is blue. Again, if you go back to the color wheel, blue is the complement of orange. So the color that you visualize is actually the color that is not absorbed, which is the complement of the color that is absorbed. Again, lycopene in tomatoes. The lambda max for lycopene is at 474, near blue region of the spectrum. That's what is going to be absorbed, and so whatever is going to be emitted is the complement. And when you look at a tomato, you see the tomato is red. And that brings us to the end of lesson 1. And I want us now to go to lesson 2. Having now looked at lesson 1 about electromagnetic spectrum, about the concept of absorption, the concept of emission of radiation, I want us now to look at how we can use this electromagnetic radiation in quantitative analysis. We've already seen we can use it for qualitative analysis. You are able to detect metals. You are able to say such a metal is present or absent based on the color of the flame.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.